Okay, okay. Okay, because you are saying that the cross sectional area is going as inverse of 1 by x square in that sense. I mean, no, area is going 1 by x, right? No, if x is the distance, the area is varying linearly in x, isn't it? No, so your area is whatever is your initial area minus some constant times x y square. Mm-hmm. Mm-hmm. But I have not given you the cross section whether it's circular or rectangular. I could as well have this one, you know, flat plates. No, this is a two-dimensional situation I am talking about. Mm-hmm. Right. Mm-hmm. Right. So this is what I have here. Okay. So if you assume that it's a circular area, then I can understand you would end up with a 2.47 number. Okay. So that's how you all were doing the problem essentially, by assuming it was a circular cross section. Okay. Now I see the point. Okay. So when I drew it like this, I assumed I'm giving you a 2D problem, which means it's a, you know, so okay. So there was a basic problem in communicating it. My mistake. All right. Anyway, the reason I wanted to illustrate this example is, now if I want to calculate the pressure drop, how do I calculate the pressure drop if it is an inviscid fluid? What is your pressure drop in this case? Rho into acceleration? Yeah. So momentum conservation. So momentum in minus momentum out, right? So how much is the momentum in and how much is the momentum out? Let's say this is air, for example. So you have 1 kilogram per meter cube. Come again? Rho 1. Okay. So rho 1 V1 square minus rho 2 V2 square. So how much does that come out to? You are right. That's where I was getting to. So then what should it be? That should be equal to P1A1 minus P2A2, right? Right. So then how do I do P1 minus P2? Mm-hmm. Mm-hmm. Right, right. So this is one equation, and the other is minus dP dx is equal to V dV dx, isn't it? Rho. Well, dV dx is a constant. So therefore, your delta P will be, you know, rho V square by 2, isn't it? Mm-hmm. Let's see. Well, if your V1 A1 is equal to V2 A2, right? So, if A varies linearly, then V has to vary linearly. What's that? Right. So, V2 by V1 is equal to A1 by A2. So, that should go as 1 by x, right? So, okay, I see your point. So, in that case, this will be some constant by x essentially, and so if you take the derivative, this will be constant by x square. Okay. Anyway, we will revisit this when we have the time for the tutorial. But what I was trying to impress on you was that because of the change in cross sectional area, you will have a pressure drop component essentially, even though the flow is totally steady. All right. Now, so if I go back to the equations that I derived in the morning, so these were the equations we derived, right. So, you have the component due to change in cross section, you have the component due to change in because of friction, this is the gravity head, and then this is the acceleration or inertia. Okay. So, at the end of the day, as a thermal designer, as a thermal fluidics engineer, what are the things I care about? I care about what is the pressure drop for a given flow rate or mass flow rate, okay. And then the other thing I care about is how much is my heat transfer, okay. So, and then what complicates the situation is you have this thing called void fraction, and so if you look in the literature, there are a lot of people who have given a lot of correlations for void fraction, okay. So, we will select a few of them, but at the end of the day, what really matters is these correlations will become a function of your flow configuration. And so, what I drew in the morning was basically this particular diagram, where your flow is going to go from subcooled boiling to, let us say, bubbly flow to slug flow to churn flow and so on, and finally you end up with mist flow, okay. And so, just before it gets to mist flow, what is known as burnout, where the surface becomes clear of any liquid, that is when the heat flux peaks, okay. And so, we talked about evaporative resistance in the morning, right. So, if I look at a corresponding flow geometry in horizontal flow with heat transfer, in horizontal flow with heat transfer, this is, you have a very asymmetric distribution of the liquid profile and the gas profiles as well. And so, if you plot the heat transfer coefficient as a function of distance, you start with a nucleate boiling dominated area when you have the onset of nucleate boiling, and as the bubble size keeps increasing, you get more and more shear near the wall, okay. So, if you go by Reynolds analogy, what does the Chilton-Colburn analogy tell you? Do you all remember what was the Reynolds analogy or Chilton-Colburn analogy? Okay. So, what Reynolds analogy tells you is, well, I will come to that in a minute, but the implication, the philosophical implication of Chilton-Colburn analogy is, if you increase your shear or pressure drop, your heat transfer has to go up, okay, or if you increase heat transfer, your pressure drop has to go up, okay. So, here because of the added shear, because of these big bubbles moving around, and you typically get flow reversal. Oh yeah, that is the other video I wanted to show you, I forgot to show you, I will show it to you after the break. You will see that there is a flow reversal that occurs, okay, where this big vapor bubble moves in this direction, but the liquid starts moving in the opposite direction, and then in the wake of the bubble they again flow back, okay. And so, all these actually cause the heat transfer coefficient to go up, and right before it dries out, you get a very thin film of liquid, and the thickness of this film is lower than the bubble diameter at departure. So, you cannot nucleate and grow bubbles at this point. So, how does heat transfer occur then? okay, then you get into film evaporation. So, now you have evaporative resistance, okay, and which is the maximum rate at which you can pump heat because of phase change. Okay, you reach the fundamental limit. So, now your limit is not how fast can you get bubbles out, because that resistance has gone out of the picture. The only resistance that remains is the fundamental thermodynamic limit, and so you get very high rates of heat transfer right at this point, okay, and right after that you get dry out. You get to a very high value and then it drops, okay, very much like your film boiling situation, where you get to CHF and then all of a sudden it goes down to almost like natural convection values, even though you are having phase change, but your heat transfer coefficient is almost the same as free convection. Okay. So, from a design point of view, you want to be as close to, in terms of the power rating of your boiler, the amount of heat you are going to feed into your system, you want to be as close to the CHF value as possible, okay, but you do not want to be exactly at that value, because if your boiler is supplying heat at this rate and your system can only pump out at this rate, then things are going to melt down, okay, just like you want to be as close to CHF as possible, but not at CHF, because then you have dry out. So, similar thing over here, you want to be somewhere, your system rating for power needs to be somewhere close to the dry out region, but maybe 10% lower or 15% lower to improve the reliability of your system, because your load always fluctuates and your system response fluctuates, and you never want your heat transfer in the system to exceed this value. Okay. So, whenever you are designing a boiling system, flow boiling system, the maximum power input into your system should not exceed this value, because then you will be in trouble, because then you will be pumping more heat, putting more heat than your system can take out. Okay. So, that is a very important consideration for design. All right. So, let us see. So, now that we understand how the fundamentals work, now we can look into the equations. Okay. So, I will not get into solving these equations, but the solution procedure is also very interesting, but you can go to the other NPTEL courses, they have it covered over there. Okay. So, I am going to just give you some summary of results over here, and then I am going to jump into condensation. Okay. So, because of the interest in time, we do not have a lot of time to get into the full details here. The handout has all the derivations, and you can look into it, and in the next 2 days, if you have any questions on the derivations, just let me know, and I can sit down with you and explain it. Okay. You got a FileX link, right? I thought some of the students, you said you got it, right? Okay, okay. Yeah, see them after the break and they can mail it to you. So, there are 3 files, one is a zip file. The zip file is a handout of all the lecture notes. Okay. So, things I have skipped, you will find it in there, and the first one is a PowerPoint, and I think the third one, what's that? Oh yeah, the third one is the live streaming link, that is right, yes. So, a couple of correlations to keep in mind. Let us see, let me fish them out. So, okay, so in order for you to solve this equation, one way to do it is to use what is known as the concept of two-phase multiplier. Okay. So, what do I mean by two-phase multiplier? It's actually a very brilliant concept to simplify a very complicated situation. Okay. So there are three sets of two phase multipliers. Remember, we talked about Martinelli parameter, right? So what did we say was the definition of Martinelli parameter? You have dp dz for fluid divided by dp dz for gas, and I'm sorry I made a mistake, it should be the square root of this. Okay, that's the definition of Martinelli parameter. So similar to Martinelli parameter, so this is for total pressure drop, right? Now if I only care about the frictional pressure drop, so the frictional pressure drop is given by dp dz friction, which is the true value of friction, divided by dp dz f. Okay, this means you are assuming that all m dot f is through the total area. Okay, then you also have something called phi FO, which is a frictional pressure drop, which I do not know, right, that is the unknown, divided by dp dz FO. And what FO means is all of the mass flow rate is assumed to be m dot f, and it flows through AT. This is easy to figure out, right? If I assume single phase flow, so let us say I have 10 kilograms per second flowing through the pipe, 2 kilograms is vapor, 8 kilograms is liquid. Okay. Now if I assume that whole 8 kilograms is flowing through the total cross section of the pipe, then it would be dp dz f. Okay, versus if I take the 10 kilograms per second and all of it is liquid and all of it is flowing through the total area, that is your dp dz FO. Does that make sense? Okay. And then you also have phi g, which is the square root of dp dz, the total frictional pressure drop for both liquid and gas together, divided by dp dz g, which means the 2 kilograms per second flows through the whole cross section. Now why do I do it? Because at the end of the day I do not know what the void fraction is at a particular location, isn't it? Okay. So not knowing what the value of void fraction is, if I can just assume that all of that flow, instead of flowing through a smaller area because of a void fraction being present, if it were to flow through the whole cross section of the pipe, that is easy to calculate, isn't it? Okay. And so then in the derivation, I will not go through the derivation right now, but in the derivation there is a little bit of a mathematical juggling act. Okay. And then after you are done with the juggling, actually the thing becomes much more simple. And so in the simplified sense, if I were to assume that it is a homogeneous flow, okay, so homogeneous flow means I am replacing that whole two phase mixture with a one fluid of one single property, and that fluid has a equivalent density which is x divided by rho g plus 1 minus x by rho f, right. That is your steam table equation. And then the other assumption is your UG is equal to UF, both your liquid phase and your gas phase are moving with the same velocity. So if I make that assumption, then automatically my void fraction calculation becomes very simple. So in that case my void fraction comes out to be x divided by rho g divided by 1 minus x by rho f plus x divided by rho g, okay, or I can write it as x times V g divided by x times V g times plus 1 minus x times V f. Okay. So once I know my void fractions, then rest of life becomes very simple. So then you can derive and show that your phi FO becomes your friction factor divided for two phase flow divided by friction factor if the whole thing was one single phase flow. Okay. And if both flows are laminar or both flows are turbulent, okay, this equation, if both are laminar or turbulent, if both flows have the same characteristic, if both your gas and liquid are laminar or turbulent, then this phi FO basically becomes your average viscosity divided by the viscosity of the fluid phase times 1 plus rho f by rho g minus 1 times x. Okay. Now, the big question is what is my average viscosity, and there is a controversy on this in the literature, because different authors tend to come up with different equations. Okay. So, one group of authors, they say, oh, it should just be this average viscosity should be just like your specific volume, x times mu g plus 1 minus x times mu f. And then another group of people said, no, dynamic viscosity is not the correct way to do it, you should be doing it in terms of kinematic viscosity. So, this is the equation that you should be using. And then another group of authors came up and said, well, it should actually be not a arithmetic mean, okay, it should be a harmonic mean. Okay. The reason is the lower viscosity component is the one that dominates the game. Okay. So, it becomes x time divided by mu g plus 1 minus x times mu f, and as far as I know, there is no resolution in the literature as far as which value of mu to use. It is a choice of your own personal flavor of ice cream. Okay. Whatever flavor you choose, like you choose and work it out accordingly. All right. So, now if you have two different flow regimes, one is laminar and one is turbulent, then life gets a little more complicated. Okay. Then this simple derivation does not hold, and so in a situation like that, people actually end up using a Martinelli correlation. Okay, let me see if I can find the correlation. Oh yeah, so when when you have a mixed flow configuration, actually let me write it out over here. So, in a mixed flow configuration, you end up with a phi f naught that looks something like this. You end up with 1 plus nu f by nu g minus 1 times x to the power of minus 0.25 times rho g minus 1 times x. Okay. That is the sort of correlation you end up with, this phi f 0 square. Okay. Now, so what is the beauty of this method? Because if I know the value of phi f 0, it is very easy to calculate this dp dz f 0, it is a single phase flow, is not it? So, I take this to the other side, I multiply these two, I immediately know what the correct value of the frictional pressure drop is, because that is the biggest enigma, figuring out the two phase frictional pressure drop. Okay. So, this gives you a very simple way of calculating the two phase frictional pressure drop, but then you are not able to use this homogeneous flow equation all the time, particularly when you have stratified flow. Your velocity of the gas phase is going to be higher typically than the velocity of the liquid phase. Okay. So, in that type of a situation, people use what is known as a separated flow model. Okay. So, in a separated flow model, oh yeah, and then the other part is a void fraction. I will come to the void fraction a little later. So, Now, in a separated flow model, okay, your dm dot dz is assumed to be equal to 0, or your ddz of ga is equal to 0, okay, and then it is a very complicated set of derivatives that you have to take, and then you have to solve for it. Okay. So, for this type of a situation, the Martinelli parameter comes in very handy. So, you can write your phi f to be equal to 1 plus c by x plus c by x square to the power of half. This is a Martinelli correlation, and then your phi g is equal to 1 plus, oh, I made a mistake, it should be 1 by x square, I am sorry, and then your phi g becomes 1 plus cx plus x square to the power of half. Okay. And the values of this c when your liquid and gas, when both are laminar, okay, or Martinelli call it its viscous flow, then the value of c is 5, and this is all based on experiments. Okay. And then when both of them are turbulent, the value of c is 20. Okay. And when the liquid phase is laminar and the gas phase is turbulent, this becomes 12, and then when this is turbulent and this is laminar, this is about 10. Okay. So, this was what was proposed by Martinelli, but there are other flavors of this same correlation, where other people put different values of these constants for different regimes. Okay. But this is actually a good enough approximation for most cases. And the characteristic of this equation is when your x approaches 0, which is you have purely liquid flow, right, which means your Martinelli parameter approaches infinity. Okay. In that case, as you expect, your phi f approaches 1 and phi g approaches x in the limit. Okay. And when you have pure vapor flow, that is x is approaching 1, your Martinelli parameter is approaching 0. Okay. In that case, your phi f approaches 1 by x and phi g approaches 1. Okay. That is the beauty of this particular correlation. It is very consistent with extension to pure liquid or pure gas flows. Okay. And remember, I talked about this instability when you go from a pure liquid to a pure vapor and you go through that instability. Okay. So, the Martinelli parameter is able to handle the not the instability itself, but the ends of those two, that curve as it goes from one flow to the other. Okay. Now, typically in a separated flow model, what you assume is if you have a flow inside a pipe, and let us say there is a gas phase and this is the liquid phase. One way to handle it is to come up with a equivalent pipe that is for gas and a equivalent pipe that is for your liquid. Okay. So, whatever is the cross sectional area of your gas phase from the void fraction, I replace it with a tube of same area. Okay. The diameter that will correspond to that area, I can replace it with a tube, and similarly the remaining part of the total area is your liquid phase. So, I replace it with a pipe with a diameter that gives me the same area as the liquid, and then I can calculate the all the flow parameters for each of these two pipes separately. Now, what is constant for these two pipes? Nope. Flow rate is constant when it is pressure drop. So, at the inlet and outlet of each of these tubes, the pressures is the same, or the drop in pressure in both the tubes should be the same for the separated flow model, isn't it? In a homogeneous flow model, both phases are traveling at the same velocity. Okay. In separated flow model, each of them are traveling with two different velocities, but at the end of the day the pressure drop going from inlet to outlet should be the same for both. So, if I impose this condition on the separated flow model, I can go back and solve that complicated equation. Does that make sense? That is a general philosophy behind a separated flow model calculation. Okay. So, in that case if I call this as RGE, equivalent pipe radius, and this is a equivalent pipe radius for liquid, then and this is R naught is the radius of this original pipe, then my RFE square by R naught square, that is equal to 1 minus alpha, and then RGE divided by R naught square, that is equal to my alpha. That is the definition of alpha. Okay. So, if I go back and substitute for all of these parameters, finally after the dust settles, okay, you end up with a correlation for the the two phase multiplier. So, your phi f square becomes 1 plus 1 by Martinelli parameter to the power of 4 divided by 5 minus n, okay, to the power of 5 minus n by 2. I will come to in a second what I mean by n. And then similarly my phi g square, and that is the beauty of this method, even without caring for the instabilities in the flow, you can simplify the solution. Okay. And then 1 plus x times 4 divided by 5 minus n times 5 minus n by 2. Okay. So, what do I mean by n? Well, if you have laminar flow and you can have turbulent flow, in laminar flow your friction factor, what did we say, was some B times Reynolds number to the power of minus n, is not it? Okay. So, if it is laminar flow, that n is 1, is not it? And if it is turbulent flow, that n is 0.25. Okay. So, that is the value of n you put in there. Now, interestingly, if both flows are laminar, okay, let us see. So, if both flows are laminar, then your phi f square becomes 1 plus 1 by x LL or x VV as Martinelli put it, to the power of 2. And if both flows are turbulent, these equations boil down to 1 plus 1 by x to the power of 16 by 19 to the power of 19 by 8. That is what it simplifies to. Okay. And then the value of alpha becomes very simple, it becomes 1 plus 0.28 times Martinelli parameter to the power of 0.7 and the whole thing to the power of minus 1. Okay. So, from a very simple set of assumptions, I can solve this very complicated equation and get some very simple solutions. That is the beauty of the separated flow model. Okay. Now, in reality, you are not going to get a very clean flow profile as we are suggesting over here. In reality, you are going to get flow reversals, you are going to get flow oscillations, and so at the end of the day, none of these assumptions account for that complication. So, you have to rely on experimental correlations at the end of the day for different flow configurations, right. So, so at for situations like that, you have to go back and look at correlations that are out there in the literature and rely on them. Okay. Now, the one I personally like, the flavor of the solutions that appeal to me, and this is just my personal preference, is what is known as the Butterworth correlation. Okay. So, the Butterworth correlation goes something like this: your alpha is equal to 1 plus a constant BB times 1 minus x by x to the power of n1, your rho g divided by rho f to the power of n2, and then mu f divided by mu g to the power of n3 whole thing to the power of minus 1. Okay. And so, different authors have given different values for this b, n1, n2 and n3. It is there in your lecture notes, but just to highlight a few of them. Okay. So, according to Butterworth, this should be let us see, actually let me put the Banerjee one essentially instead of the Butterworth. So, the Banerjee correlation is probably the most universally applicable, and so Banerjee came up with these values of 1, 0.74, 0.65 and 0.13 based on his experiments. And if you believe Lockhart and Martinelli, so Lockhart gave these to be 0.28, 0.64, 0.36 and 0.07. Okay. And see, these guys did experiments under different conditions, under different diameter of tubes, and came up with different numbers. Okay. So, now the question is, when do you use homogeneous model and when do you use separated flow model? Okay. So, in my handout in the lecture notes I have this table here, and this is actually a good guide. So, when you have homogeneous, when you have bubbly or mist flows, at the very beginning of the two phase flow process or at the very end of the two phase flow process, it is a good idea to use homogeneous flow, because bubbles are so small or the mist droplets are so small, they travel at the same velocity as the bulk. Okay. Now, if you have round tubes, fin geometries, low pressures, adiabatic or flow boiling essentially, then you use the Martinelli and Nelson correlation. Okay. Interestingly, Banerjee correlation actually applies to both bubbly flow and separated flow, okay, and it has pretty wide applicability, and the variation between your true value and the predicted value is of the order of 20%, which is pretty good, considering two phase flow literature. Okay. So, if you have no idea, go with Banerjee. Okay. Banerjee correlation is a good starting point for doing an estimation. Okay. So, now that I have the pressure drop part figured out, the next part is figuring out the heat transfer, right. Now that I know what size pump I need, what kind of pressure drop I will need. So, pressure drop times your flow rate gives you the pump power, and then you assume your motor has a certain amount of efficiency, and you calculate all the pump efficiencies, you plug it in, divide your theoretical power divided by the net efficiency, you get what kind of pump motor you will need, what size pump you will need, right. So, the pressure drop part is calculated. So, the next part is how long a pipe do I need, right, for a given flow rate to go from pure liquid to pure steam. That is the next question I want to answer, okay, which means at each and every segment of that pipe I need to calculate the heat transfer coefficient. Okay. So, there are a lot of heat transfer correlations out there. In the interest of time, I will just highlight one. The one I like the most is known as the Chen's correlation, okay, and there are a bunch of other ones, they are there in your handout, you can look into it. And so, when it comes to predicting the net heat flux, okay, what Chen proposed was the heat transfer in two phase flow, he broke it up into two parts, H micro plus H macro. Okay. This is good, I think. Yeah, it's okay. So, now what did he mean? What he meant was, if you look at boiling occurring in a pipe. Okay. So, let us say you are in fully developed nucleate boiling. Okay. The interesting thing about fully developed nucleate boiling is it is almost independent of the orientation of the heater. Okay. Whether you have a horizontal heater, a inclined heater, it does not matter, you will get almost the same value of fully developed nucleate boiling. I am not talking about critical heat flux. Okay. CHF is sensitive to orientation, and of course, your onset of nucleate boiling is sensitive to orientation, but in between the whole phenomena of two phase boiling, essentially two phase flow or boiling in a pool boiling sense, is very insensitive to the variation in this orientation and your heater geometry and all these things. Okay. Which means, if I push the liquid out of the system, okay, the fully developed nucleate boiling heat transfer coefficient is not going to change much. Okay. So, that is what he called as the H micro. Okay. So, my heat transfer Q double prime will be equal to H times delta T, which is H times T wall minus T sat, right. So, the H micro is almost independent of flow rate, it is very less sensitive to flow rate, this tends to be constant. Whether I push liquid at 1 meter per second or 2 meters per second, this H micro will probably vary by 10%. Okay. So, this is the insensitive part, and then the macro is your sensitive part. So, typically if you have turbulent flow, what correlation do I use in a turbulent flow in a pipe? How do I estimate the Nusselt number? Any of you know? So, Dietz-Boelter correlation, right. So, if I write down the Dietz-Boelter correlation, it is what 0.023 Reynolds number to the power of 0.8, Prandtl number to the power of what? Come again? So, in this case what do we have? Do we have heating or cooling? So, this should be 0.3, right. And as you can see over here, if you double the flow rate, my Reynolds number goes twice, right, and so my heat transfer coefficient goes roughly 0.8 is close to 1. So, my heat transfer coefficient will sort of double. Okay. So, that is my macro. Okay. So, that is the idea behind the Chen's correlation. Okay. And when I discuss the flow boiling on carbon nanotube coatings, you will see that this correlation actually comes very close to predicting the values that we were getting. Okay. So, what I mean by that, so let us say I look at my total heat transfer, right, Q double prime, and so if I plot my Q double prime as a function of my flow rate in a pipe, the total flow rate I am talking about, the H micro or the Q micro will be very insensitive, it will be a curve that looks like this. Okay. But my Q macro will sort of look like this. Does that make sense? So, therefore, my Q total will look like this. So, what do you see? The proportion of the total heat flux that comes because of boiling is going to shrink. Does that make sense? Yeah, as I go to higher and higher flow rates, the amount that is coming from boiling, the proportion, the fraction is going to shrink. is not it? Now, what happened was when we put carbon nanotube coatings, the Q micro jumped and it became almost double. So, this is my Q micro with CNT. My Q macros stayed almost the same, it did not care whether you had carbon nanotube coating or not. Okay. Later on Friday, when I go through all the results for the micro and nano, you will see that trend. Okay. And so, what happened as a result was, initially at low flow rates we see a very high enhancement because of carbon nanotubes are present, is not it. So, in essence my Q total now, instead of starting here, started here, and so the enhancement I saw in the boiling heat transfer was higher at lower flow rates, and the percentage enhancement that I saw decreased as the flow rate kept increasing. Okay. But we are not measuring the Q micro, what we are measuring in our experiment is the Q total, is not it, and then we are looking at the Q total without nanotubes versus Q total with nanotubes. And what we see is this graph is actually not parallel, I drew it a little wrongly. So, in reality what the graph looked like was, I mean these are estimates, right, the micro and the macro, these are estimates. In reality what I am measuring is I am measuring just the Q total. So, this is Q total without nanotubes, and this is the Q total with nanotubes, and you can see the enhancement is very high at low flow rates, and the enhancement is decreasing as the flow rate is increasing. And the only way you can explain this data is if Chen's correlation is valid. Does that make sense? Yeah. All right, let us take a tea break and let us come back in 10 minutes, and we will start with condensation. So, the minimum heat flux that we covered for pool boiling yesterday, I think there might have been a typo when I was writing it on the notes, and I might have missed this rho g square in the denominator. So, just go back and check the correlation that I wrote yesterday, and if I am missing the rho g square, just add that rho g square in the denominator. Okay. So, that is just the correction from the notes yesterday. Now, when it comes to condensation, as I mentioned on the first day, that there are two types of condensation regimes that you typically look at. One is the film condensation, which is shown on the diagram on the right hand side, where you have a vertical plate and you have a pure vapor that is coming in contact with a cold flat plate, and you can have either a constant heat flux or sort of a constant temperature boundary condition, and in essence you form a thin film of condensate that increases in thickness as you go down. Okay. Now, this typically happens if the surface is wetting, okay, which means the contact angle is less than 90 degrees for that particular vapor or liquid. Now, if you have a surface which has a very low surface energy, remember we talked about the Lennard-Jones potential, that A by r to the power 6 minus B by r to the power 12. So, those A and B parameters depends on how much energy the surface has in attracting the fluid molecules. So, if you have a very low energy surface, then the attraction between the molecules of the same type, the fluid molecules, is higher than the attraction from the wall to the fluid molecules. Okay. So, as a result, the resultant effect is these droplets, they tend to form almost spherical type of structures rather than a film. In the case of film boiling, because the attraction of the solid for the fluid is much higher, it spreads out, because the fluid is not able to keep the fluid molecules together, because the attraction between the fluid molecules is less than for the attraction from the solid surface to the fluid molecules, right. So, once you have droplet condensation, you have very discrete droplets that form on the surface. Okay. Now, which one do you think has a higher internal pressure, a smaller droplet or a bigger droplet? Smaller droplet, right. So, if I have a small droplet and a big droplet and both of them are condensing vapor on them and they are both growing with time, at some point they are going to touch each other. Okay. So, will the small droplet get inside the big droplet or will the big droplet move into the small droplet? Okay. Why would the small droplet move into the big droplet? Because the pressure inside the small, the sigma by r pressure is higher in the small droplet and flow always occurs from a high pressure to a lower pressure. And so, what happens is the big droplet cannibalizes the small droplet. What does that do to the heat transfer? When the droplet merger happens, does the heat transfer go up or go down? Okay, why does it go down? The surface energy decreases. Why should the surface energy decrease? So, two droplets essentially, right. Okay, but does the condensation occur on the top of the droplet? Where does the condensation occur? So, condensation occurs when the vapor comes in contact with the solid, right. So, the condensed droplet is an extra resistance that slows down your condensation rate. So, the more exposed surface I have, the more condensation I will have, right. Now, does the condensation happen uniformly on the surface? Okay. So, the same nucleation theory that we looked at, remember we talked about nucleation of droplets, the same nucleation theory applies also for condensation. Okay. You are not going to get droplets of all of different sizes. Okay. There is a minimum droplet size that forms, and if your droplet size is smaller than that minimum size, it will disappear, it will not sustain itself, just like for nucleation of a vapor bubble, unless it is bigger than a certain critical size, it will not survive. Okay. So, similar principles hold. Now, so that brings into the question, what does the heat transfer coefficient profile look like on a surface? Okay. So, and here is the interesting thing, there is a very similar situation whether you have nucleate boiling, film boiling or droplet dropwise condensation. A very similar transport phenomena happens in all these three cases. Okay. What do I mean by that? So, let us draw the nucleate boiling case first. Okay. So, let us say I have a small cavity. Oh, sorry. So, let us say I have a small cavity and I have nucleated a vapor bubble on top of it. All right. So, that is my nucleate boiling situation. Now, let us look at a film boiling type of situation. And as I mentioned, in film boiling you get a profile that looks like this, right. So, let us start with the film boiling. So, if I think about the heat transfer in film boiling, how is the heat transfer occurring? It is by conduction and radiation, right. Radiation is almost uniform, but your conduction heat transfer will not be uniform. So, wherever I have a minimum thickness in the vapor film, that is where I am going to have the highest heat transfer, is not it? Okay. So, in other words, the heat transfer coefficient at any location is proportional to k by delta, the k of the vapor, kg by delta, is not it? So, wherever delta is small, your heat transfer coefficient is high, wherever your bubble is thick, the heat transfer coefficient is small, is not it? Because the amount of path that the heat has to travel through is much longer, and therefore, virtually the area under the bubble is insulated. These places are almost insulated boundary heat transfer, essentially insulation boundary condition. So, if I go back and if I plot the heat transfer coefficient, okay, how would the heat transfer coefficient look like? Well, your delta T is constant, is not it? It is always T W minus T sat. So, if I plot the heat transfer coefficient, I will get the inverse profile of the bubble of the vapor film. So, if I plot the heat transfer coefficient is going to be really low under the bubble. It is going to peak like a delta function, okay, and that is how the heat transfer coefficient is going to look like, is not it? So, turns out this peak heat transfer coefficient is of the order of kilowatts per centimeter square at these locations, whereas over here you are looking at something like maybe about 10 watts per meter square Kelvin. Okay. And over here you are looking at very low values, something like 5 watts. I mean, I am talking about the heat transfer, I am not the heat transfer coefficient, I am sorry. Okay. So, because the heat transfer coefficient looks like that, my total heat transfer is also going to have a profile, the heat flux is also going to have a profile similar to my heat transfer coefficient. Okay. So, the peak heat transfer is going to be of the order of kilowatts per centimeter square or 10 to the power 4 watts per meter square. So, effectively the rest of the surface is insulated, is not it? And I have these zones where it is like a delta function of very high heat transfer. That is how film boiling operates, all right. So, as a consequence, how is the temperature profile going to look like? So, if I plot the temperature profile, wherever I have a peak in the heat transfer, I am going to get a dip in the temperature, is not it? So, my temperature is going to look something like so, that is how my temperature profile is going to look like. So, this value of temperature will be something like, let us say if your boiling is at 373 Kelvin, for water you need about 100 degrees Celsius to sustain film boiling, superheat. Okay. So, this temperature will be of the order of 475 to 500 Kelvin, okay. Whereas, this temperature here, okay, you are looking at will probably dip by a factor of about 30 Kelvin. This cold spot that is formed, a lower temperature region, so this temperature drop can be as high as 30 Kelvin. Okay. So, similarly I can do it for nucleate boiling also, and the reason I am doing this is you will see there is a direct correspondence when it comes to condensation. Okay. So, if I plot the heat transfer coefficient, again in this particular case, the point at which I have the liquid vapor triple point that is connecting with the solid, okay, that location I will get a peak heat flux, because if I magnify this region under the bubble over here, I get what is known as a micro layer. Okay. So, if I magnify this area, if I look at the heater surface, this region where the liquid vapor triple point happens, it looks like this, where constantly your liquid is coming in and it's vaporizing in a thin film. The thin film evaporation we talked about, you get a sort of a thin film evaporation in the, so this zone is known as the micro layer. Okay, and there is a controversy in the literature. Many people have theorized different values of the thickness of this micro layer. So, there are reports, some people say, oh, this micro layer should be, if I look at the thickness of this micro layer, some people say delta E is about 1 micron to 100 microns. Okay. Ivan Catton at UCLA, his theory is it's of the order of 100 nanometers. Okay, so, you can see in the literature there is a wide range that people are predicting. The problem is nobody has measured it, because if it is 100 nanometers, it is below the wavelength of light, and most of the time what people do is they use interference fringes using visible optics. So, if you are using visible optics, your resolution is down to 300 nanometers. So, if your thickness goes below 300 nanometers, particularly below 100, you can still go to lambda by 2, about 150 with some corrections. Okay. So, if your thickness is below 150 nanometers, then you are totally clueless, right. And so, what people do is they measure up to about 100, about 300 to 400 nanometers, and then they do a asymptotic, they draw a asymptote and they say, oh, at this location it goes to 0 thickness, and so it should be about 100, about 300 or 500 nanometers in thickness, and that is erroneous. Okay. Now, we will revisit this micro layer concept a little later, but the whole point of it is at this point you get a peak in the heat flux or heat transfer coefficient. So, if I were to do the same kind of plot, if I were to do the heat transfer coefficient plot, the heat transfer coefficient will peak at this triple point, and then here you have a single phase heat transfer, it is solid to liquid, right. And so, single phase heat transfer in a liquid, you are looking at 10 watts per centimeter square. Here it is heat transfer from a solid to a gas, you are looking at 5 watts per centimeter square, and it again peaks over here and goes to 10. That is my heat transfer coefficient profile, or heat, or you can say my Q also has a very similar profile essentially. Okay, now, the big enigma is what is this peak, and so there are some estimates by a French group. They are saying that this peak can be as high as 100 watts per centimeter square. Okay. But the problem is it is in a very narrow area, it's the area is of the order of 50 to 100 microns. Okay. So, if I had the eyes of a snake, snake can see IR, right, they can see heat. So, if I have a hot piece of iron lying on the ground, unless I touch it, I will not know whether it is hot or not, but a snake can figure it out, because they can see infrared radiation. So, if there is a hot piece of iron and a cold piece of iron, they can immediately distinguish the two, because they can see in the IR. It is like they have a IR camera going around with them. So, if I were to take a IR camera and if I were to look on a boiling surface, what would I see? Every time I see a bubble, I see a toroidal shape where the temperature is lower than the rest of the heater, and as the bubble is wobbling around, that cold spot is moving around with the bubble. You see, if I were to visualize it, right, and where is the cold spot? It is in the circumference of that contact region. Okay. So, every time I form a bubble, okay, the bubble will have a contact on the heater surface, isn't it? So, wherever it is contacting, that is the location where I will see a cold spot. Now, what is the significance of this cold spot? More than half the total heat transfer is occurring there. Okay, so, if I want to enhance boiling, all I have to do is either increase the contact line or increase the number of bubbles, right. So, the more the number of bubbles, more the contact point, more the delta function in the heat transfer, because effectively this is a delta function, isn't it. Wherever there is a cold spot, there is a high value of heat transfer, you know, and wherever there is no cold spot, it goes to like 5 or 10 versus 1000. So, effectively it is a delta function. Okay. So, now that I understand how it happens for, you know, nucleate boiling and film boiling, let us look at how it happens when it comes to condensation, because this has an implication in terms of the condensation heat transfer. Okay. So, there are certain aspects with condensation that are a little different than boiling. Okay. So, let us look at that. So, let us say, you know, when I have condensation occurring on a surface, I typically get a fractal structure. We get it in boiling also, we will talk about it on Friday, and hopefully if I have time I will discuss more details about it. But if I look at a surface where condensation is happening, what I will see is I will see a bunch of big bubbles or big droplets. Okay. And then right around each of these big droplets I will see smaller droplets. So, there is a parent droplet, and around each parent droplet there are child droplets. Okay. And around each child droplet you will see a bunch of even smaller droplets that are the grandkid droplets. So, which one do you think is pumping the largest amount of heat per unit area? The parent droplet, the child, or the grandchild? Why? Okay. So, there are two things that are happening, because the thickness of the liquid layer is smaller. So, they have less resistance. So, they are getting more condensation rate, and then if you have a big droplet, the majority of the condensation is on the perimeter, isn't it, just like in boiling. You will get a peak in the heat transfer right at the perimeter, and the smaller droplet actually has higher perimeter per unit mass, isn't it. So, there are two, you know, transport mechanisms that are helping you. Does that make sense? Okay. At the end of the day, it is still TW minus Tsat, but how that TW minus Tsat is getting broken down into smaller and smaller parts makes a big difference. Okay. So, that is one part, and then each of these droplets are growing, and then of course, the smaller droplets are growing at a faster rate than the bigger droplets, because they are having a higher rate of condensation, and then at some point these smaller droplets are getting eaten up by the bigger droplets. Okay. So, these are child eating droplets, right. So, so then, you know, and then each of these droplets, as they grow bigger, they are getting consumed by the even bigger droplet. Okay. So, that is one process, and at some point, you know, nothing is perfectly horizontal, right. There will be a little inclination somewhere or other, and so at some point the droplet rolls off, and in the process of rolling it takes other droplets with it as well. It consumes a bunch of droplets, goes away, and the whole process keeps repeating. Okay. So, you can see right away that in condensation very quickly a fractal network forms. Okay. A fractal network is nothing but a self similar network, where the same pattern keeps repeating at smaller and smaller scales. So, I have one droplet with 4 child droplets, and I look at the child droplet, it has 4 grandkids with it, and I look at a grandkid and it has 4 great grandkids with it, and so that same structure, it is kind of like a tree. You know, a tree branches off into 2 branches, and then you go on that branch, it branches off into 2. So, it is kind of like that. Okay. So that way it forms a fractal network. All right. Now, which one do you think gives you a higher heat transfer, for film boiling or droplet, dropwise condensation? I mean, film condensation or dropwise condensation? Dropwise condensation gives you a higher heat transfer, right? Then why do most of the engineering systems use film condensation? Why is it unstable? Is it really unstable? That's the first question actually. So dropwise condensation is very unreliable. It has a great performance. If you are looking for domestic help, what are you looking for? You are looking for the domestic help that comes every day, right? Not the help that comes one day, gets all the job accomplished in 1 hour, but you don't know whether he is going to come the next day or not. That's not the domestic help you want, right? The domestic help you want maybe is a little inefficient, but at least you are assured that this guy will come every day. That's the same thing with dropwise condensation. Okay, so whenever you get surfaces with very low surface energies, they tend to be very unreliable, because they tend to get fouled very quickly. Okay, and part of the reason is there is always pollution in the air, you always have grease in the air, and because these surfaces have low surface energy, they tend to deposit the grease from the ambient, and once the grease deposits over time, they become more and more wetting. Okay, so low energy surfaces are actually susceptible to contamination. Okay, so one object that leverages low energy surfaces very well is actually the leaf of a lotus. Okay, lotus leaves actually have very low energy, effectively they have low surface energy, and the way they achieve it is they have a lot of nanoscale pillars that stick out of the leaf, and so therefore they are able to suspend the droplets on top of those small fins that stick out from the leaf, and they are very good at regenerating those nanoscale pillars, micro and nanoscale pillars, because it is a living object, so it is able to regenerate itself, versus if you have a plastic surface, okay, if it gets fouled or if it gets degenerated, it is not self generating surface, right. So that is where the problem comes with dropwise condensation, that it is very unreliable. It is a very good performing surface. If you can guarantee the reliability of the surface, then it makes more sense to use it. Okay. But the main problem is, number one, fabricating these surfaces is very difficult. Okay. Coming up from one batch to next, coming up with the same surface energy is very difficult, and then the second is, over a longer time period, guaranteeing that you have the same performance over a certain period of time is also very difficult, because you have a lot of fouling and corrosion. Okay. And so that is why dropwise condensation has not found as much use in engineering applications. All right. Now let us look at the how this heat transfer coefficient profile, how this plays out in a real world. Okay. So if I look at a fractal surface like this, and if I were to plot the temperature profiles and so on, so let us say I have a surface like this, and I have a bunch of droplets. I have a big droplet, I have a smaller droplet, I have even a smaller droplet, right. I am going to get a whole distribution of droplets going from big to small and then small to big, right. And so if I plot the heat transfer coefficient profiles, or the heat flux profiles, of course the heat fluxes will peak wherever I have a liquid vapor solid triple point, isn't it. So this is my heat flux profiles. And they are going to be almost uniform, because that triple point will have almost same values of heat transfer coefficient. Okay. So, what is that going to do to my temperature profiles? So, my temperature profiles, they are going to be very closely spaced. So this is how my heat flux lines are going to look like. It is kind of like flowing of water. A lot of heat is coming through this small area and then it is spreading out, isn't it? So that is how my heat flux lines will look like. It is kind of like water flowing from a small conduit into a big conduit. Okay, so keep that in mind. All right. So at the end of the day, I am going from T sat over here to T wall over here, isn't it? But is it really T wall here? It is probably not, because my temperature is fluctuating wildly, isn't it? Wherever there is a high condensation, my temperature is going up, and wherever there is a droplet, the temperature is coming down. It is the opposite of boiling. So it is probably not T wall over here, it is some other value T w prime, which is higher than what your T wall actually is. So your T wall is somewhere down here. You see what I am saying? Okay. So therefore your total temperature drop, which is T w minus or T sat minus T w, okay, has three components. There is a delta T interface, there is a delta T due to capillarity, and there is a delta T for what is known as constriction resistance. Okay. So I have a resistance at the interface, a thermal resistance at the interface. I have a thermal resistance due to the droplet, and I have a thermal resistance because it has to conduct from here to here. You see what I am saying, which is known as the constriction resistance. Now, is this resistance uniform? It is not, because my heat flux lines are constricted here, my heat flux lines are spread out here. If it was uniform heat flux lines, then it is very easy to calculate this R constriction. Okay. So you have one resistance for this heat to travel from the pure vapor to this interface, that is your interface resistance, and then there is this other resistance which is for the heat to flow from within the bubble or within the droplet, that is your capillary resistance. And after it has crossed the droplet, it still has to go a certain distance before it hits T wall. So if the heat flux lines were uniform, okay, then it is very simple. It is whatever is this thickness divided K divided by this thickness, right. That would have been my nominal resistance, but because the heat flux lines are constricted and expanding, your actual resistance is going to be higher than the pure conduction resistance, okay, because of the non uniformity in your heat flux lines and the temperature lines, because it is not a uniform linear drop in the temperature. The temperature drop is going to be nonlinear, and because the temperature drop is nonlinear, your del T del y or your del T del x, that gradient is going to be actually higher. Okay. And so because of that, your constriction resistance is much higher than your normal thermal resistance. Does that make sense? Okay. So the sum total of these three resistances, or each of these resistances will have a potential drop across them, and so those are the potential drops. Okay. And that at the end of the day is equal to T sat minus T w. Okay. So what is the heat flux I am going to get? I am going to get a heat flux because of del T I divided by R I. I am going to get a heat flux because of delta T cap divided by R cap, and then I am going to get a delta T constriction divided by R constriction. Okay, so those are the 3 individual drops that you have to encounter. Okay, now contrast this with film condensation. In film condensation, it is fairly simple because I have the heater surface. I think I dropped my pen. Okay, I will have a film of liquid, and I might have some ripples on this film of liquid, okay, and ripples will increase your heat transfer. I do not have time to go through it, it is there in your handout. You will see there is one section where it discusses the effect of the ripples. The ripples can actually improve your heat transfer by a factor of about 10% versus when you do not have ripples. Okay. So, but that aside, this is fairly straightforward because I will have a resistance at the interface. This is my interface resistance, this is my capillary resistance, and typically your constriction resistance is almost negligible. Okay, so your total heat transfer is your total delta T, which is T sat minus T w, and that is divided by the interface resistance but plus the capillary resistance, the resistance due to that thin film. And so the constriction resistance is not as much of a factor as it is for droplet condensation. Okay, you all with me on this? Okay, now since we are discussing the recent topics in multi-phase flows, how does a carbon nanotube coating affect this heat transfer? Okay, so the dynamics is very interesting. So we made a microchannel heat exchanger, and in a microchannel heat exchanger, of course, your liquid film will grow as you go along the direction of the heat exchanger, isn't it? Okay, so I have a heat exchanger and I have these microchannels built into it, and the vapor is coming into the system. Okay, on the back side I am cooling it using water, and so if I look at the profile of the thickness of this condensate film, this condensate film is going to let me redraw it actually. So if I am looking at it in the side view, if this is my channel cross section, the vapor is coming in from this direction. As the refrigerant is condensing, this film is growing, isn't it? And at some point it is going to be a pretty thick film, right? And so if I plot the heat flux, or I plot the heat transfer coefficient in the direction of the flow, I am going to get a very high value of heat transfer, and it is going to rapidly go to 0, because at some point the resistance in the film is so high that you do not get as much heat transfer anymore. Okay. So the trick is to capture the heat transfer. So more than 50% of the heat transfer is probably in the first 10% of your heat exchanger. You see the problem, right? The bulk of the condensation or heat transfer that is occurring very close to the entrance region of the heat exchanger. So now if I put a carbon nanotube coating in there, okay, so initially if my carbon nanotube is sticking out like this as a fin, at some point the carbon nanotube loses its effectiveness because it is buried under the liquid film. Okay, where is the carbon nanotube most effective? Wherever it comes directly in contact with the vapor, because carbon nanotube is effectively at the same temperature as the wall. Okay. So the carbon nanotubes that are exposed in this region are the ones that are the most effective. Okay. So we did a project where the goal was overall heat transfer coefficient, which is 1 by H1 plus 1 by H2, right. If you have a heat transfer between two flowing liquids on one side of a solid, right, that is your heat exchanger principle, right. So, the overall heat transfer coefficient is heat transfer on the hot side and the heat transfer coefficient on the cold side of your flow, and plus of course, you have the conduction resistance because of that metal layer in between, but this one is usually neglected. And so, the goal was to get a U which was 50 kilowatts per meter square Kelvin, which means my H1 and H2 both of them have to be at least 100 kilowatts per meter square Kelvin. That was our target H for the refrigerant side. Okay. Once we put the carbon nanotube coating in there, so we built it without carbon nanotube coatings to meet that criteria. Okay. So, without the carbon nanotube coatings, we were able to get about 100 kilowatts per meter square Kelvin. The moment we put carbon nanotube coating, the condensation heat transfer coefficient went to 250 kilowatts per meter square Kelvin, more than what we had asked for. Okay. So, but then we figured the carbon nanotubes were only effective only for that first 10% of the heat exchanger. So, if you were to redesign the whole thing, instead of making a long heat exchanger, we would make it a fat heat exchanger, okay, where the width will be high, but the flow direction length will be small. Okay. So, if you were to design a heat exchanger for condensation or boiling, okay, keep in mind that the major part of the heat transfer will be only in the first 10 to 20% of your heat exchanger. All right. So, you got to design it as a small length with a big width rather than with a small width and a long length. Does that make sense? Okay. So, I think we are already above time today, and let us call it a day today. I guess it is already 5, right? What time is it? 5:15. Okay. All right. So, tomorrow Dr. Das and Dr. Bhattacharya will be conducting. They are going to look at some more advanced topics like boiling on porous media and so on, rewetting and those kind of applications. And Friday I am going to give you a more comprehensive condensed, because we have been discussing the micro and nano parts in bits, right. So, my goal is on Friday to bring all of it together and give you a complete picture. Okay. So, there will be a 2-hour long lecture just exclusively focused on micro channels, nano channels, and then boiling on nanostructures, nano sensors. I did not get to talk about the metrology. Okay. So, I am going to talk a little bit about metrology as it comes to micro and nanoscale flows. Okay. So, thank you and see you tomorrow.